Here is something that should recalibrate everything you think you understand about the material world. Right now, in this moment, the atoms in your body are almost entirely nothing. The nucleus of a hydrogen atom, a single proton, is roughly 100,000 times smaller than the atom itself. Scale the atom up to the size of a sports stadium, and the nucleus becomes a marble sitting at the center of the field. The electrons orbit in the upper tiers of the seating. Everything in between is empty. Not empty the way a room is empty when the furniture has been removed. Empty the way deep space is empty. There is nothing there. No substance, no medium, no ether, no fabric filling the void between the nucleus and the electrons. You are made almost entirely of empty space. And yet, you are not falling through the floor. The floor is almost entirely empty space as well. You and the floor, both vast voids of nothing with a few particles scattered through them at enormous relative separations, are pressing against each other with a force your muscles know without needing to calculate. The solidity you feel through your feet right now, the resistance, the weight, the certainty that the floor is there and will remain there, is not produced by anything touching anything else in any classical sense. It is produced by quantum mechanics, by forces acting between particles that are not in contact, by fields, by probability distributions, by the consequences of laws that operate at a scale so far below the threshold of human perception that bridging the two requires a chain of physical reasoning more than a century in the making. Here is what makes this genuinely worth your attention, not as abstract curiosity, but as a fact about what you are. The particle physics that explains why solid matter is solid, why you do not pass through walls, why the floor holds your weight, why the atoms in your cells can form the chemical bonds that make biology possible, is the same physics that explains why matter exists at all, why the early universe produced more matter than antimatter, why protons do not decay on timescales shorter than the age of the solar system, and why the universe that contains you is constructed the way it is rather than some other way. The structure of matter from the quarks inside protons to the atoms those protons build to the chemistry those atoms perform to the biology that chemistry makes possible is one continuous thread. Pull on any part of it, and you pull on all of it. This is the story of what matter is actually made of, where it came from, why it behaves the way it does, and what the deepest experiments in human history have found when they pulled that thread as hard as current technology allows. The long descent into smallness. For most of human history, the question of what matter is made of was answered at the level of things that could be seen or felt. Earth, water, fire, air, the classical elements of the ancient world were not naive proposals. They were empirical observations about the categories of matter as experienced: solids, liquids, gases, and heat. The person proposing them was not stupid. They were working with the data available. The first serious move toward something smaller came from Democritus in the 5th century BCE, who proposed that matter was ultimately composed of indivisible particles he called atomos, the Greek word for uncuttable. The idea was arrived at by argument rather than experiment. If you keep cutting matter in half, you either reach a smallest piece that cannot be further divided, or you do not, and matter is infinitely divisible. Democritus argued for the first option, but he could not demonstrate it. The atomic hypothesis was philosophically interesting and experimentally invisible for the next 2,000 years. The modern atomic theory emerged in chemistry in the early 19th century. John Dalton in 1803 proposed that elements were composed of characteristic atoms with specific masses, that compounds formed by combining atoms of different elements in fixed ratios, and that chemical reactions involved rearranging atoms rather than destroying or creating them. This was not a philosophical claim. It was an organizing principle that made precise, testable, verifiable predictions about the mass ratios of chemical reactions. The table of elements that Dmitri Mendeleev organized in 1869 revealed periodicities in chemical properties that made no sense unless atoms had internal structure that repeated with a pattern through the table. But what that structure was remained opaque. The first breach came in 1897. Joseph John Thomson, working at the Cavendish Laboratory in Cambridge, was studying cathode rays, the streams of charged particles produced when a voltage was applied across a vacuum tube. By measuring how these rays deflected in electric and magnetic fields, he determined the ratio of their charge to their mass. The ratio was the same regardless of what material the cathode was made from. The particles were universal, the same from every element. They were lighter than the lightest known atom by a factor of nearly 2,000. They carried negative charge. Thomson had discovered the electron, the first subatomic particle, the first evidence that atoms were not indivisible after all. What this implied about the structure of atoms was initially unclear. If atoms contained electrons, and electrons were negatively charged, and atoms were electrically neutral, then there had to be positive charge in there somewhere. Thomson proposed the plum pudding model, a diffuse sphere of positive charge, with electrons embedded in it like currents in a pudding. It was a reasonable hypothesis. It was wrong in a way that turned out to be spectacularly revealing. In 1909, Ernest Rutherford at Manchester directed a stream of alpha particles, which are helium nuclei carrying 2 units of positive charge, at a thin sheet of gold foil. The expectation based on the plum pudding model was that the particles would pass through with minor deflections, like bullets through a fog. Instead, a small fraction of them bounced back almost directly. Rutherford described his reaction by saying it was as if you fired artillery shells at tissue paper, and they came back and hit you. What the experiment proved was that the positive charge in atoms was not diffuse. It was concentrated in an extraordinarily small, extraordinarily dense nucleus at the center, a nucleus that contained almost all the atomic mass in a volume 100,000 times smaller than the atom itself. The rest of the atom was the vast emptiness that you are made of. Rutherford's model, a dense positive nucleus with electrons orbiting it at large relative distances, was the architecture of the atom. It explained the scattering results precisely. It created an immediate new problem. Classical electromagnetism said orbiting electrons should radiate energy continuously and spiral into the nucleus in a fraction of a nanosecond. Real atoms do not do this. Something was preventing the collapse. The resolution of that problem required a completely new framework for understanding the behavior of matter at small scales, a framework that turned out to describe a universe stranger than anyone had been willing to accept before the data forced it. The quantum revolution and what it found. In 1913, Niels Bohr proposed that electrons in atoms occupy specific discrete energy levels rather than a continuous range, and that they emit or absorb light only when jumping between levels, releasing or absorbing a photon whose energy equals the difference between levels. This explained the spectral lines of hydrogen. the precise, discrete colors of light that hydrogen emits when excited, with extraordinary accuracy. But it explained them by assertion rather than derivation. Bohr said electrons occupy stable orbits without justifying why those orbits should be stable. The justification came from Louis de Broglie in 1924, who proposed that matter, like light, has a wave nature. Electrons are not just particles. They are also waves, with a wavelength inversely proportional to their momentum. Bohr's stable orbits were the orbits in which the electron's wavelength fits exactly an integer number of times around the circumference. The orbit is stable because the wave reinforces itself constructively. Other orbits are unstable not because of a rule, but because the wave interferes destructively with itself and cancels. This was the first glimpse of why matter at small scales obeys quantum rules rather than classical ones. The discreteness is not imposed by fiat. It emerges from the wave nature of the electron constrained to a finite region. Erwin Schrödinger, in 1926, turned this into a full wave equation. The Schrödinger equation describes how the wave function of a particle evolves over time and in space. The wave function is a mathematical object whose squared magnitude gives the probability of finding the particle at any given location if a measurement is made. The electron in a hydrogen atom does not have a definite location. It has a probability distribution, a cloud of possible positions, denser where it is more likely to be found and sparser elsewhere. The orbital shapes that chemists draw, the spherical s orbitals, the dumbbell-shaped p orbitals, the more complex d and f orbitals, are not electron paths. They are maps of probability density. This was philosophically unprecedented and remains, despite decades of successful application, deeply uncomfortable to those who think carefully about what it means. The electron is not somewhere specific until you measure it. Before measurement, it exists in a superposition of all the positions the wave function assigns non-zero probability to. Measuring it does not reveal where it was. It causes the wave function to collapse to a definite position. What was diffuse becomes specific in the act of observation. The act of measurement is not passive. Werner Heisenberg's uncertainty principle follows from this. The more precisely you determine a particle's position, the less precisely you can know its momentum, and vice versa. This is not an engineering limitation. It is not that our measuring instruments are too clumsy. It is that position and momentum are complementary quantities that do not simultaneously have definite values. The universe does not provide both at once. The uncertainty is ontological, not epistemological. It is in the world, not in our knowledge of it. This framework, quantum mechanics, is the most precisely tested theory in the history of science. Its predictions have been confirmed to extraordinary levels. The anomalous magnetic moment of the electron, a measure of how strongly the electron behaves like a tiny magnet, is predicted by quantum electrodynamics to agree with measurement to 11 decimal places. No other scientific theory has achieved this level of precision. Quantum mechanics is not a speculation or an approximation. It is the operating system of the material world at small scales, confirmed by every experiment that has ever been designed to test it. Inside the nucleus. The picture, by the early 1930s, was atoms composed of electrons orbiting a nucleus, with the nucleus containing protons, which carried positive charge, and neutrons, discovered by James Chadwick in 1932, which carried no charge and approximately the same mass as protons. The atomic number, the number of protons, determined the element. The mass number Protons plus neutrons determined the specific isotope, but this picture immediately raised a severe problem. The nucleus is extraordinarily small, and the protons inside it are all positively charged. Positive charges repel each other with a force that scales as the inverse square of the distance between them. Pack several protons into a nucleus whose diameter is a few femtometers, a femtometer being 10 to the negative 15 meters, and the electrostatic repulsion is enormous. There had to be something stronger holding the nucleus together, a force that was attractive at very short range and strong enough to overcome the electrical repulsion of the protons. This force, eventually named the strong nuclear force, was the subject of intense theoretical and experimental investigation through the 1930s and 1940s. Hideki Yukawa proposed in 1935 that it was mediated by a particle of intermediate mass that he called a meson, predicting a mass of roughly 100 mega-electronvolts. A particle roughly matching this description, the pion, was discovered in 1947 in cosmic ray experiments by Cecil Powell. The exchange of pions between nucleons, the collective name for protons and neutrons, was the mechanism of the strong force at the nucleon level. But the deeper structure was still not understood. The 1950s and 1960s produced an explosion of particle physics discoveries as accelerators became powerful enough to probe higher energies. Dozens of new particles appeared, all of them strongly interacting, all of them with apparently comparable claims to being fundamental. The situation became sufficiently chaotic that some physicists spoke of a particle zoo, an embarrassing proliferation of entities when the goal was a clean, economical description of nature. The resolution of the zoo emerged from a combination of theoretical insight and experimental determination. Murray Gell-Mann and Yuval Ne'eman independently noticed in 1961 that the known strongly interacting particles could be organized into geometric patterns according to a symmetry group called SU3, in a way that strongly suggested these particles were not themselves fundamental, but were composite objects built from a smaller number of more fundamental constituents. Gell-Mann named the hypothetical constituents quarks, from a line in James Joyce's Finnegan's Wake. He identified three types, which he called up, down, and strange, with fractional electric charges of 2/3 and -1/3. Protons were composed of 2 up quarks and 1 down quark, neutrons of 2 down quarks and 1 up quark, pions and the other mesons of a quark paired with an antiquark. The symmetry patterns of the particle zoo fell into place as the expected combinations of these three building blocks. In 1964, Gell-Mann predicted the existence of a particle, the omega-, whose properties could be specified precisely from the quark model. It had not yet been observed. It was found shortly afterward at Brookhaven National Laboratory with the mass and quantum numbers the model predicted. This was the moment the quark model became serious. Prediction, followed by experimental confirmation, is the core of how physics advances, and the omega- was a clean example. The deeper mechanism of the strong force, the force that binds quarks inside protons and neutrons, was not the pion exchange that worked at the nucleon level. It was something more fundamental. Quarks carry a charge that has nothing to do with electromagnetism, a color charge, a term of art with no connection to visible color, with 3 possible values conventionally called red, green, and blue. The force between color charges is mediated by particles called gluons, massless carriers of the strong force. The theory describing this interaction is quantum chromodynamics, QCD, and it has a property unlike any other force in physics. The strong force does not weaken with increasing distance the way electromagnetic and gravitational forces do. It remains roughly constant. This has a remarkable consequence. When two quarks are pulled apart, the energy in the gluon field between them increases. Eventually, there is enough energy to produce a new quark-antiquark pair from the vacuum. The pair materializes, each new quark binds to one of the original quarks, and you end up with two mesons rather than two free quarks. Free quarks do not exist in normal conditions. They are confined inside hadrons always. This confinement is why the quark model took time to be taken seriously. If quarks cannot be separated and isolated, how do you know they are there? The answer came from deep inelastic scattering experiments at the Stanford Linear Accelerator Center in the late 1960s. Electrons fired at protons at very high energies behaved as though they were scattering off point-like objects inside the proton, rather than a smooth, continuous charge distribution. The data matched almost exactly what the quark model predicted. The quarks inside the proton were real. They were just permanently enclosed. The standard model and what it explains. By the 1970s, the pieces were assembling into what became known as the standard model of particle physics, the most successful theoretical framework in the history of science, describing the fundamental constituents of matter, and three of the four known forces with a precision that has not been exceeded by any competing framework. The matter particles in the standard model are fermions, particles with half-integer spin. They come in two families: quarks, which feel all three non-gravitational forces, the strong, weak, and electromagnetic, and leptons, which do not feel the strong force. There are 6 quarks: up, down, charm, strange, top, and bottom, arranged in 3 generations of increasing mass. The up and down quarks make up the protons and neutrons of ordinary matter. The heavier quarks exist briefly in high-energy collisions and in the early universe, but are unstable and decay rapidly to lighter forms. There are 6 leptons: the electron, the muon, the tau, and their associated neutrinos, again in 3 generations. The electron is stable and constitutes the outer structure of atoms. The muon and tau are heavier, unstable copies of the electron. Neutrinos have almost no mass, interact almost not at all with ordinary matter, and travel through solid matter as if it were not there. The force-carrying particles are bosons, particles with integer spin. The photon mediates electromagnetism. The W and Z bosons mediate the weak nuclear force, responsible for certain types of radioactive decay. 8 types of gluons mediate the strong force. The graviton, if it exists as a quantized particle, would mediate gravity, but gravity has not been successfully incorporated into the quantum framework and remains outside the standard model. The Higgs boson, discovered at CERN's Large Hadron Collider in 2012, is the particle associated with the Higgs field, a field that permeates all of space. Particles that interact with the Higgs field acquire mass proportional to the strength of that interaction. Particles that do not interact with it, the photon and gluons, are massless. Without the Higgs mechanism, all fundamental particles would be massless. Matter as we know it could not form, and the universe would be an undifferentiated soup of radiation. The Higgs field is what gives mass to the things that have it, and the discovery of the Higgs boson confirmed that the field exists. The standard model has a relationship to experiment that is without precedent in science. Its predictions have been confirmed to extraordinary levels across an enormous range of energies and conditions. The mass of the W and Z bosons calculated before their discovery, confirmed when they were found. The existence and properties of the top quark predicted from theoretical consistency requirements, confirmed when it was discovered at Fermilab in 1995. The anomalous magnetic moment of the electron calculated to 11 decimal places, confirmed to that precision. The decay rates of the Higgs boson into various final states, predicted from first principles, confirmed in the LHC data, within measurement uncertainties. The Standard Model is not a phenomenological summary of what has been observed. It is a predictive framework that has correctly predicted what would be observed before the observations were made, repeatedly, across decades. And yet, the Standard Model is certainly incomplete. It does not include gravity. It does not explain the mass of neutrinos, which the model originally predicted to be zero, but which have been confirmed to be small, but non-zero. It does not explain why there are 3 generations of matter particles, rather than 1, or 2, or 17. It does not explain the values of its own parameters, the masses of the quarks and leptons, the strengths of the forces, which must be measured and inserted rather than derived from any deeper principle. And it does not explain the observation from cosmology that ordinary matter, the stuff described by the Standard Model, constitutes only about 5% of the universe's total energy content. The antimatter asymmetry. Of all the puzzles surrounding the Standard Model, one of the deepest is also one of the most personally relevant. Why do you exist? This is not a philosophical question. It is a precise physical one. The laws of physics, as currently understood, treat matter and antimatter as almost perfectly symmetric. For every type of particle, there is a corresponding antiparticle with the same mass but opposite charge. The photon is its own antiparticle. The antielectron, the positron, has the same mass as the electron but positive charge. The antiproton has the same mass as the proton but negative charge. When a particle and its antiparticle meet, they annihilate, converting their combined mass energy entirely into photons or other particle-antiparticle pairs. In the Big Bang, the conditions were right to produce matter and antimatter in essentially equal quantities. The temperature in the first fractions of a second was so high that the thermal energy available was sufficient to create particle-antiparticle pairs from the photon gas continuously. Protons and antiprotons, electrons and positrons, quarks and antiquarks materialized and annihilated in a continuous frenzy of creation and destruction. As the universe expanded and cooled below the threshold temperatures for creating each pair type, creation stopped, but annihilation continued. Every proton found an antiproton and annihilated. Every electron found a positron and annihilated. If matter and antimatter were produced in perfectly equal numbers, the final state of this process would be a universe of pure radiation, pure photons and neutrinos, with no residual matter particles at all. No protons, no electrons, no atoms, no chemistry, no planets, no biology, nothing. Instead, there was a slight excess of matter over antimatter. The current best estimate is that for every 10 billion antiparticles produced in the Big Bang, there were 10 billion and 1 particles of matter. After annihilation, that 1 particle in 10 billion was left over. And those leftover 1 in 10 billion particles are every atom in your body, every star in every galaxy, every observable structure in the universe. You are the residue of a fractional asymmetry. Your existence depends on the fact that the laws of physics treat matter and antimatter not quite identically. The conditions for this asymmetry to develop were identified by the Soviet physicist Andrei Sakharov in 1967 and are known as the Sakharov conditions. Three things must be true simultaneously. There must be interactions that violate baryon number conservation, the rule that the total number of matter particles minus antimatter particles is constant. There must be interactions that treat matter and antimatter differently, a property called CP violation. And these processes must occur out of thermal equilibrium so that the imbalance produced is not immediately erased by the reverse process. The Standard Model contains CP violation. It was first observed experimentally in 1964 by James Cronin and Val Fitch in the decays of neutral kaons, particles containing strange quarks. The amount of CP violation in the Standard Model is measurable and confirmed, but it is not large enough. The CP violation in the Standard Model can produce a matter-antimatter asymmetry of perhaps 1 part in 10 to the 18th. The observed asymmetry is 1 part in 10 billion. The Standard Model is short by about 8 orders of magnitude. Something is missing. There is CP violation in the universe beyond what the Standard Model accounts for. Every particle physics experiment probing the properties of matter particles with high precision is, in part, a search for the additional source of CP violation that explains why you are here, rather than a universe of featureless radiation. The Bell 2 experiment in Japan, measuring the properties of particles containing bottom quarks to unprecedented precision, is looking for deviations from Standard Model predictions that would indicate a new source of CP violation. The searches have not yet found the answer, but they are narrowing the range of possibilities with every data set. The hierarchy problem and the desert. There is a number in the Standard Model that is technically natural, but deeply suspicious. The mass of the Higgs boson, measured at 125 gigaelectronvolts at the LHC, is a free parameter, a quantity that must be inserted rather than derived. By itself, this is not unusual. Many parameters in the Standard Model must be measured. What makes the Higgs mass suspicious is the way quantum corrections behave. In quantum field theory, the measured mass of a particle is not the same as the bare mass that appears in the Lagrangian, the fundamental equations of the theory. Quantum corrections, contributions from virtual particles that exist briefly as quantum fluctuations, and then disappear, shift the measured mass from the bare mass. For most particles, these corrections are manageable. They are proportional to the particle's mass itself, so a light particle gets small corrections and remains light. For the Higgs, the situation is different. The quantum corrections to the Higgs mass are proportional not to the Higgs mass itself, but to the square of the energy scale at which the Standard Model is assumed to remain valid. If the Standard Model is valid up to the energy scale at which gravity becomes quantum mechanical, the Planck scale at roughly 10 to the 19th gigaelectronvolts, then the quantum corrections to the Higgs mass are of order 10 to the 38th gigaelectronvolt squared. The observed Higgs mass is 125 gigaelectronvolts. To get from a correction of 10 to the 38th to a measured mass of 125 requires a cancellation between the bare mass and the corrections to 34 decimal places. Not approximately. Exactly 34 decimal places. This extreme cancellation is technically possible. There is nothing logically inconsistent about it, but it has the character of a conspiracy rather than a physical law. It requires the parameters of the theory to be fine-tuned to an extraordinary degree without any mechanism explaining why they should be so fine-tuned. This is the hierarchy problem, and it is one of the most pressing theoretical motivations for physics beyond the Standard Model. The leading proposed solution for decades was supersymmetry, a theoretical extension of the Standard Model in which every particle has a superpartner with the same mass but opposite spin statistics. Fermion superpartners are bosons, and boson superpartners are fermions. The corrections to the Higgs mass from supersymmetric partners cancel the corrections from the Standard Model particles up to the mass splitting between the particles and their superpartners. If supersymmetric partners exist near the TeV scale, the fine-tuning problem is resolved. The Higgs mass is technically natural. The Large Hadron Collider was in significant part designed to find supersymmetric partners. It collides protons at energies up to 13 TeV, well above the mass range, where the simplest supersymmetric models predicted the lightest superpartners should appear. After collecting and analyzing data from millions of collision events over more than a decade, no supersymmetric particle has been found. The simplest models have been largely excluded. More complex models remain viable, but require increasingly baroque parameter choices that undermine the naturalness argument that motivated supersymmetry in the first place. Other proposed solutions exist. Extra spatial dimensions beyond the three we experience, accessible to gravity but not to Standard Model particles, could lower the effective Planck scale and eliminate the hierarchy. Composite Higgs models, in which the Higgs is not a fundamental particle, but a bound state of more fundamental constituents, could explain its properties dynamically. The relaxation, a proposed scalar field that scanned through possible Higgs mass values in the early universe and locked in the observed value through a cosmological selection mechanism, is another possibility. None of these has been confirmed experimentally. The hierarchy problem remains open. What the experiments have not found. There is a way of telling the history of particle physics that makes it look like a story of unbroken triumph. The Standard Model predicted a particle. Experiments found it. The prediction was confirmed. The model was vindicated. Science advanced. This telling is accurate as far as it goes, but it omits something important. The Large Hadron Collider, the most powerful particle accelerator ever built, operating at energies that span a range of conditions approaching those of the universe when it was a picosecond old, has found exactly one new particle since it began operations. The Higgs boson, the particle whose discovery completed the Standard Model. Everything else the LHC has searched for, it has not found. Every supersymmetric particle, not there. Every Kaluza-Klein graviton from extra dimensions, not there. Every new gauge boson from extended symmetry groups, not there. Every dark matter candidate accessible to high energy production, not there. This is not a failure of the accelerator. The LHC has performed magnificently. The experiments are sensitive, the detectors sophisticated, the data analyses careful. The absence of signals is a genuine physical result. It is telling us that the territory above 100 giga-electron volts and below roughly 3 tera-electron volts, which is the range the LHC has explored, contains the Higgs boson and the Standard Model particles, and nothing else measurable by the experiments that have been run. The physics community is in a position that is historically unusual. The experimental frontier has expanded enormously and found no new physics beyond what was already known. The theoretical landscape is rich with proposals for what should be there. The data says it is not there, at least not where it was expected. This is forcing a reconsideration of which theoretical priors were reliable guides and which were wishful thinking, dressed as theoretical insight. The next generation of accelerators being designed and proposed would extend the energy reach by a factor of several. The proposed Future Circular Collider at CERN would collide electrons and positrons at 365 giga-electron-volts in a first phase, measuring the properties of the Higgs and other particles with much greater precision than the LHC, and then collide protons at 100 TeV in a second phase, extending the energy frontier by a factor of roughly 8. The International Linear Collider proposed for Japan would be an electron-positron machine at up to 1 TeV. These projects are decade scale, requiring the construction of tunnels and detectors of unprecedented scale, and they are motivated not by the expectation of a specific discovery, but by the recognition that the range of energies they would probe has not been explored, and something unexpected might be there: the dark matter that is not in the detector. 27% of the universe's total energy content is dark matter. This is not a loose estimate. It is a tightly constrained value derived from multiple independent observations, the rotation curves of galaxies that Vera Rubin's work made clear, the gravitational lensing of light from distant galaxies by intervening mass, the pattern of temperature fluctuations in the cosmic microwave background, the large-scale distribution of galaxies, the formation history of cosmic structure. Every one of these observational probes gives a consistent answer: roughly 27% dark matter, 5% ordinary matter, 68% dark energy. The 5% that ordinary matter constitutes is the standard model. The other 95% is outside it. Dark matter is whatever provides the gravitational scaffolding for cosmic structure. It neither emits nor absorbs light. It does not participate in electromagnetism or the strong force. It is affected by gravity, and the arguments are strong that it is a particle, or a class of particles, that is heavy enough to be non-relativistic and therefore cold, clustering under gravity to form halos around galaxies. The leading candidate for decades was the weakly interacting massive particle, the WIMP, a particle with mass in the range of a few giga-electron-volts to a few tera-electron-volts and interaction cross-sections comparable to those of standard model particles with the weak force. WIMPs were theoretically attractive for a specific reason beyond just fitting the observations. They arose naturally in supersymmetric extensions of the standard model and in a wide class of other motivated theoretical frameworks, and their predicted relic abundance from the early universe, calculated using the standard tools of thermal cosmology, came out in the right range to explain the observed dark matter density. This coincidence was called the WIMP miracle, and it was persuasive enough to drive a generation of experimental programs. Direct detection experiments placed large volumes of target material deep underground, shielded from cosmic rays and other backgrounds, and waited for the rare event of a dark matter particle colliding with a nucleus and depositing a small amount of energy. The experiments ran for years, accumulated enormous exposures, and found nothing. The LOX Zeppelin experiment in the Homestake Mine in South Dakota, the most sensitive direct detection experiment currently operating, has searched a parameter space that covers the entire region where the original WIMP miracle arguments predicted dark matter should be detectable. The detector has not found it. The Axion, a much lighter candidate particle originally proposed by Roberto Pache and Helen Quinn in 1977 to solve a separate problem in QCD, the absence of CP violation in the strong force, which is itself puzzling given that nothing obviously forbids it, has mass in the range of microelectron volts to millielectron volts, far too light for the detectors searching for WIMPs. Experiments like ADMX and CASPER use precision electromagnetic techniques to search for axion conversion into photons in strong magnetic fields. These searches are ongoing and sensitive, but have not yet found a confirmed signal. The identity of dark matter is one of the deepest open questions in fundamental physics. Whatever it is, it makes up more than 5 times as much of the universe as all ordinary matter combined. Every atom in your body is embedded in a dark matter halo of roughly equal density to the rest mass of the stars in the Milky Way, but distributed in a roughly spherical cloud, extending far beyond the galaxy's visible disk. Dark matter is passing through you right now, through your walls, through the earth beneath your feet, through the entire planet, at rates that depend on its interaction cross-section. And it is invisible to every biological sense you possess, and to most of the detectors ever built. What we do not know, the honest account of particle physics, has open questions at every level, and they should be stated plainly. We do not know what dark matter is. The evidence for its existence is overwhelming and comes from multiple independent observational sources. Its particle identity is completely unknown. Every leading candidate that has been experimentally searched for has either been excluded or remains undetected in the parameter space where it was most expected. The range of viable candidates spans decades in mass and many orders of magnitude in interaction strength. There is no consensus on which of these candidates is most likely to be correct. We do not know why there is more matter than antimatter. The asymmetry that explains our existence requires CP violation beyond what the standard model contains. The source of that additional CP violation has not been identified. Every experiment looking for it is searching in the dark, in the sense that the theoretical target is not precisely specified. We know the asymmetry exists. We do not know its mechanism. We do not know why the Higgs mass is what it is. The hierarchy problem, the extreme sensitivity of the Higgs mass to quantum corrections from physics at high-energy scales, has not been resolved. No new physics has been discovered at the LHC that provides a natural stabilizing mechanism. The most popular proposed solutions, supersymmetry and compositeness, have not been confirmed. The standard model may simply be unnaturally fine-tuned in a way that has no deeper explanation, or the explanation may lie in the energy range above the LHC's reach that has not yet been probed. We do not know how to incorporate gravity. The standard model describes electromagnetism, the strong force and the weak force within a unified quantum field theory framework. Gravity, described by Einstein's general relativity, resists this unification. The two frameworks are fundamentally incompatible. General relativity treats space-time as a smooth, continuous dynamic geometry. Quantum field theory requires a fixed background space-time. Quantum gravity, the framework that would describe gravity as a quantum theory, does not exist in a complete tested form. Candidates exist. String theory proposes that particles are not points, but one-dimensional extended objects, resolving the ultraviolet divergences that plague point-particle approaches to quantum gravity. Loop quantum gravity treats space-time as fundamentally discrete at the Planck scale. Neither has made a confirmed, testable prediction that distinguishes it from the alternatives. We do not know why there are 3 generations of matter particles. One generation containing the up quark, the down quark, the electron, and its neutrino is sufficient to produce all the stable ordinary matter in the universe. The second and third generations, containing copies of this structure at higher masses, exist, decay to the first generation, and played roles in the early universe. No known theoretical principle requires exactly 3 generations. The pattern might be a coincidence of the initial conditions of the universe. It might be a consequence of a deeper symmetry not yet identified. We do not know what caused the initial conditions of the early universe. Inflation, the rapid, accelerated expansion in the first fraction of a second after the Big Bang, explains the large-scale uniformity and flatness of the observable universe and is supported by measurements of the cosmic microwave background. But inflation requires an inflaton field with specific properties and a specific potential energy function. No candidate for the inflaton has been identified in particle physics. The mechanism that started inflation, sustained it, and ended it at the right moment is unknown. The floor beneath your feet revisited. Go back to the room. Feel the floor beneath you. The solidity that your feet report through the soles of your shoes, the resistance, the permanence, the certainty that the floor is there and will not give way. You know now what that solidity actually is. The atoms in your feet and the atoms in the floor are almost entirely empty space. The nuclei at their centers are protons and neutrons built from quarks bound together by the exchange of gluons, a force so strong that free quarks have never been observed in the low-energy conditions of any experiment. The electrons surrounding those nuclei are not particles in a classical sense, but quantum fields, probability distributions, smears of possible location with no definite position until something interacts with them. The solidity your feet feel is quantum electrodynamics. The electromagnetic force between the electrons in your feet and the electrons in the floor, operating through the exchange of virtual photons that exist for intervals far shorter than any measurement can resolve, generating the Pauli exclusion principle that prevents 2 electrons from occupying the same quantum state, producing the effective repulsion between electron clouds that makes matter impenetrable to other matter at normal energies and pressures. The force that is holding your weight up right now is not a contact force in any classical mechanical sense. It is a quantum field effect, a consequence of the wave nature of electrons, the discrete quantization of atomic energy levels, and the statistical property of half-integer spin particles that forbids them from sharing states. None of these things were part of the physics available to human understanding before 1900. All of them were discovered by experiment in the 20th century against the expectations of classical intuition. The quarks in those protons have been carrying the same quantum numbers since before the solar system formed. The up quarks in the protons in the iron of the Earth's core have been up quarks since the supernova that seeded the solar system's heavy elements 4.5 billion years ago. Their properties, their mass, their charge, their color charge, their spin have not changed and will not change. They are carrying a signature of the conditions that produced them in the early universe, a period when the temperature was high enough that quark-gluon plasma was the dominant state of matter, and the distinctions between quark generations were not yet frozen in. The electrons in the atoms of your body are carrying quantum numbers that link them, through the chain of particle physics, back to the electroweak symmetry-breaking transition in the first picosecond of the universe's history, when the unified electroweak force separated into the electromagnetic and weak forces, and the Higgs field acquired its non-zero vacuum expectation value, and mass began to mean anything at all. You are standing on matter that has been exactly what it is since before the Earth existed. The quarks and electrons that make up the floor have been quarks and electrons since the universe was seconds old. Their properties are determined by a set of parameters in the standard model that must be measured and inserted by hand, because we do not know why they have the values they do rather than other values. The theory that describes them is the most precisely confirmed scientific framework in history. It is also certainly incomplete, missing the explanation for dark matter, for the matter-antimatter asymmetry that allowed matter to exist at all, for the mechanism that gave the Higgs its mass, and for the reconciliation of quantum mechanics with gravity that would constitute a true fundamental theory of everything. The floor is solid. The physics that makes it solid is confirmed to 11 decimal places. The physics beyond the floor, the framework that would explain why the parameters take the values they do, why there is matter rather than antimatter, what constitutes the 27% of the universe that holds galaxies together, remains one of the deepest unsolved problems in science. We are standing on matter we understand in extraordinary detail and not completely at all, simultaneously, right now, at every moment, without any sensation to distinguish between the two. Matter is almost entirely empty space that behaves exactly like it is not. The quarks inside the protons in the floor beneath your feet have never been free and probably never will be. The electrons preventing your feet from passing through that floor are not anywhere in particular until they interact with something. The Higgs field permeating the space around you right now is what gives all of them their mass. And 95% of the universe is something else entirely, outside the standard model, outside any confirmed theoretical framework, present everywhere, shaping everything, and still unnamed. The floor holds. The questions remain open. Both of these are the most interesting things currently happening in physics, and they are happening simultaneously in the same place, which is everywhere you can look. You have been watching the entire history of the universe. Do not forget to like and subscribe, and leave a comment to let us know what you think. Thanks for watching, and we will see you next time.